In this case, we're asked the question, how much energy is needed to heat 16 grams of ice from 0 degrees C to 30 degrees C? First step on these is identify where you start. So we know we have 16 grams of ice, so ice is this very bottom section down here, but it says the ice is at 0 degrees C. And so ice at 0 would start right here. So we're going to start right there. That's actually the beginning of the melting section. And it tells us the ice is heated from 0 degrees C to 30 degrees C. So 30 degrees C is going to be up on the liquid water section. So we've got two sections we're going to cover. We're going to cover the melting section where we take it from 0 degree ice to 0 degree water, and we have the heating section where we take it from 0 degree water up to 30 degree water. In order to solve this, since it covers two different sections, we're going to have to split this into two parts. We're going to have to say, we're going to go from where it starts melting to where it ends melting. That's going to be our Q1. And then we're going to go from where it starts heating to where it ends heating. That's going to be our Q2. And so then once we've got those two, we can add them up, and that'll give us the total energy, the total heat that's needed to heat them up. So we're going to start off with Q1. We look at Q1, and Q1 is on a section where basically the phase is changing. Since the phase is changing, we're going to have to use MHL, or in this case it'll be MHF, because of the fact that this is the heat of fusion we're dealing with here. And so we say Q1 is MHF, so Q1 is equal to the mass, 16 grams right here, times the heat of fusion for water, which is 79.7 if you look that up on your colored sheet. And so if we do the math on these, get out your calculators, and you can say that Q1, it would be 16 times 79.7, and you get 1275.2. Notice we're not going to do any rounding just yet. We'll do that at the very end. And so that's going to be Q1. Q2 is our second section. So since it is up on this part right here, that the temperature is changing, we're going to use Cm delta T. Q equals Cm delta T. And so for this, we say Q2 is equal to C. Since we're on the liquid water phase, we know that C is equal to 1 right there by looking at your colored sheet. So we have 1 times the mass, which we found before, 16 grams, times delta T. In this case, we have to look at only the temperature change on the section we're interested in here. And in this case, we started at 0, we ended at 30. And so our temperature change is just 30 degrees C. In this case, it happened to be the overall temperature change, but you want to watch out because that's not always true. You just have to look at what the temperature change was on only the section that Q2 applies to. And so we're going to get this out, and so we say 16 times 1 times 30, and so when you do that, you get 480. And so we get Q2 is equal to 480 calories. Now to find our final Q, we know that Q is equal to Q1 plus Q2, like that. And so from here, we'll say our final Q is going to be equal to Q1, which we found to be 1275.2, plus our Q2, which is 480. And when we do that, we get a final Q value of, we add those up, 1275 plus 480, we get 1755.2. Now, if we look at our original values here, we had two significant figures on Q1, which should take us to the, if we do that, that's at the hundreds place right here. On Q2 is we had two significant figures. That takes us to the tens place. Since we're adding these, the least significant one here is the hundreds place here, so we're going to round this to the hundreds place. So our final answer here is going to be 1800. If we round the correct number of significant figures, that's 1800 calories. And so that's what we have for our final answer on this one. So as you can see, to solve one of these, you simply want to figure out what are the heats for each section. First, go ahead and figure out what the heat is for Q1 right in here. That's what we did here first. And then figure out the heat for Q2 right here for our next one. And then add those up, and that will give you the total answer right down there. So let's take a look at another one that's a little more complex, and see what we can do there. So continuing on this, it says a sample containing 2 grams of negative 15 degrees C ice has 6.9 kilocalories of heat added. What is the final temperature of the sample? And so let's look at where we start. So it says we have negative 15 degrees Celsius ice. So negative 15 degrees is going to be down here. And so that's where we're going to start. And it says we end where? A sample containing 2.0 grams of ice has 6.9 kilocalories of heat added. What's the final temperature? We don't know the final temperature. We don't know where this ends up. And so as a result, what we're going to have to do is we're going to have to see how much energy it takes on each of the sections. And then once we found how much energy on each of the sections, we're going to find how far we have to go to use up all our energy. So our total energy here is 6.9 kilocalories. 6.9 kilocalories is 6,900 calories. Kilo is 1,000, remember? And so we know that the 6,900 kilocalories is going to be equal to Q1 plus Q2 plus Q3 plus however many Qs we have. It might just be Q1. We don't know. It might be Q1 and Q2, might be Q1 and Q3. It might be all the way up through Q5. Because if you look at it, we could have it, since we have 5 sections, we can have as many as possibly 5 different Qs on a calculation like this. But the only one we know that we're on is we do know that we're on this first section down here on the ice section. And so we know that we have a Q1. And so Q1 is going to be the first one we're going to deal with. And so let's set this up with Q1. And so we say that Q1, since the temperature is rising, is equal to Cm delta T. And so in order to do this, then we would say that let's assume in this case, to start with, that this will go all the way up to the very top of the ice section, which would be right about there. It would go from negative 15 degrees Celsius all the way up to 0. If it turns out that we end up using more energy than what we've got, then we'll have to go back and basically plug in the energy we started with and then solve for the change in temperature. But if it's less than the energy that we use up, the energy we have available is 6.9 kilocalories, then we'll just subtract that off of the total and then see how much we have left. Basically what we're doing is every time we cross a section, we subtract that from the total, see how much we have left until we run out of energy. And so here we use Q1 equals Cm delta T. In this case, C, because of the fact this is ice, is going to be, if you look on your color sheet, is 0.53 times the mass, which is 2, times delta T, which we said we're going from negative 15 to 0, so that's just 15. And so if you get out your calculators on that one, you can see that we have 0.53, oops, I got to clear that off, 0.53 times 2 times 15. And so when you do that, you get 15.9. And so I get that Q1 is equal to 15.9 calories. So I had 6,900 to start with. So have I used up my full 15.9? Absolutely not. And so I know I've got at least 15.9 that's here. And I'm going to have to add that to the amount of energy that's on my second section. Second section is going to be going across here. It's going to be going from the point where we're basically melting this ice. And so we're melting the ice here. And so I know I at least have a Q2 that's involved. So my Q2 is going to be equal to, since it's just a phase change, it's going from ice to water, it's melting, it'll be MHL. So the mass here is going to be 2 grams, same as it was before. The HL that's here is going to be the one that's actually HF, because of the fact that we're melting the ice, it's heat of fusion, and that's 79.7 if you take a look at your colored sheet. And so we add these up, or we multiply them out. So we say 2 times 79.7. When we do that, we get 159.4. So 159.4 here. And so we know that 159.4, have we used up all of our heat? Not even close still. We have 15.9 plus 159.4. We still clearly have a lot of energy that's left here. And so we'll go on to our next section, which is Q3. The maximum this could go would be to go all the way up to the very top of our water section, which would be a change from 0 degrees all the way up to 100 degrees. And so let's take a look at that one here. Q3 is, since the temperature is changing, is going to be equal to Cm delta T. The specific heat for water is 1 times M, which is the mass is 2, times delta T. We said we were going from 0 all the way up to 100, which means we have a delta T of 100 degrees. And so if you do this, you get 200. So Q3 is just equal to 200 calories. Still, we have not gotten anywhere close to our total here. We're nowhere close to 6,900, so we really don't even have to do any math with that. We just know we're not there yet. Our next segment we could possibly go would be going all the way across here. Would be going from wherever it started as water and that when it boils off. And so if that previous one was our Q3, this one here will be our Q4. And so that one is going to be a phase change. So Q4 is going to be equal to MHL. And so the mass once again is 2 times HL. In this case, it's going to be HV, and HV for water is 539. And so when we do this out, we get Q4. Excuse me. It'd be 2 times 539, so you put that in your calculator, 2 times 539. And so this equals 1,078. Certainly a lot larger than our previous ones. But still, 15 plus 159 plus 200 plus 1,000, that's not even close to 6,900. But we only have one section that's left. That's this very last steam section right here. We know that has to be a Q5, but do we know how much that is? Well, we sort of do, because we don't know what Q5 is, but we do know that if we add it to those other heats, it has to equal 6,900. And so since that's the one that's left over, we can go ahead and take 6,900 and we can subtract off the existing heats we have. So minus 15.9 and then minus 159.4. And then we're going to subtract off 200 and then we're going to subtract off that last one, 1,078. When we do that, we find we have 5,446.7 left. So I know that Q5 is equal to 5,000, what is it? 5,446.7. calories. So if I know how many calories Q5 is, I also know that Q5 is a section where basically we're talking about specific heat. The temperature is rising here. So I'd say 5,446 is equal to C, which for gaseous water, for vapor, is 0.48, times M, which is 2, times delta T. And so from this, I can go ahead and solve for delta T. So I take my 5,446 and I would divide it by 0.48 and divide it by 2. And so by doing that, I end up with a total of 5,000, my delta T is 5,673.6 degrees Celsius. Now, so that's my change in temperature. Well, change in temperature from what? Change temperature from where we started here. We started at 100 degrees Celsius, and so since we started with 100, we've got to add 100 plus the 5,673 plus 100 degrees. So we have a final temperature of 5,773.6 degrees. We're told that 17,000 calories will heat what mass of 25 degrees Celsius water to 150 degrees Celsius? So first step is we need to figure out what regions this is going to cover. And so let's take a look at our heating curve. And so we were told that it starts at 25 degrees C and it ends at 150. And so if we start at 25 degrees C, that means we're starting like right about here. We're ending at 150. That's like way up here. And so we know we're going to have to at least have 3 sections here. We're going to have Q1, from basically from 25 degrees up to 100. We'll have a Q2 that goes whenever we're basically boiling it off. And then we have a Q3 that's going to go from 100 degrees up to 150 degrees. So a change of a delta T of 50 degrees. And so this is what we know we're going to have to set it up. So 3 Qs involved here. And so, whoops, bring that back to where it was. So 3 Qs that are involved here. And so let's set this up. We know that we have Q1, and Q1 is equal to Cm delta T. And so we know that since it's on the liquid phase, that the C is going to be 1 times the mass, which we don't know, so we leave it as M, times delta T. We're going from 25 degrees to the top of the liquid phase, which is at 100 degrees. That's just going to be 75, because 100 minus 25 is 75. And so then from that, we find that Q1 is going to be equal simply to 75 M. Okay? Q2 is going to be whenever we're on the vaporization phase. And so the vaporization phase is MHL, or MHV in this case. So we take the mass times basically whatever the vaporization constant is, HV is, which is for water, 539. And so from this, we just get 539 M. That's Q2. Q3, we're back onto its phase where the temperature is rising, so we're looking at specific heat. So Cm delta T. C for a vapor is 0.48. times M, which we don't know, times delta T. So we're going to 150 degrees Celsius, but the vapor phase starts at 100. And so we'd say 150 minus 100 for our change in temperature. So 100 minus 150, or 150 minus 100 just gives us 50. And so we go ahead and take that in the calculator, and we say 0.48 times 50, and we get 24. And so that means we know Q3 is just equal to 24 m. We know that our total Q is going to be equal to Q1 plus Q2 plus Q3. And so total Q here is 17,000 calories. Bunch of calories here. And that's equal to Q1, which is 75 m, plus Q2, which is 539 m, plus Q3, which is 24 m. So we can take these guys and add them up. So we'd say 75 plus 539 plus 24. And so we get that 638 m. So 17,000 is equal to 638 m. Divide both sides by 638. And so we find that our mass here would be 17,000 divided by 638. So we take 17,000 our calculators and divide it by 638. And so I get 26.64. And so we have two significant figures to start with. So we'd say 27 grams of water that are here. And so if we added 17,000 calories to 27 grams of water at 25 degrees Celsius, it would end up exactly at 150 degrees Celsius. And that's how you work out a problem where you don't know the mass on all of them. And so that finishes up this lesson.